Hello and welcome to Diksha Karnataka YouTube channel. So as you all have requested that sir I need recorded session, so that's why I am recording this session. I was supposed to take this live, but because of my unavailability I am not able to take this class as live, so that's why it is being recorded. Now remember, if you have any doubts, don't forget to mention that in the comment section below so that I can address them as soon as I am available. Now very important point is that this is the third part of electrostatic potential and capacitance, and if you are wondering sir what happened with the other two parts from this chapter, it is already been telecast as live. I was there as live, so you can go and check that out in the playlist section. That playlist section will contain your first chapter as well as the other two parts from this chapter as well, right? And obviously we will also have our AIO page there, all in one page. You can go and check that out. The description section, you can click on the all in one page as well. Now let's start. So basically what all we are going to discuss in today's session, just a second. So we have already covered electric potential and capacitance in our previous chapter. So if you are wondering what we have all covered, so electrostatic potential, potential energy and potential, point charge, system of charges, equipotential surface, relationship between electric field and potential, potential energy due to system of charges, potential energy due to dipole. This all everything is covered in our part 1. So if you are looking for some concept from there, you can check our part 1. Now conductors and dielectrics, what is conductors, what is dielectrics, what is polarization, that is covered in our part 2. And lastly but not least, capacitor, everything related to capacitor that we are going to discuss in today's session. This is our part 3, and then there will be a session for PYQs as well. So don't worry, we will be covering everything that is possible. Now let's look into what is a capacitor. So capacitor is a device that is used to store charges. So the main purpose of capacitor is storing charges. Okay, it does not store anything else, it only stores charge. So that's why it is called capacitor. Capacitor means it has a capacity. So capacity to hold capacitance, charge is called capacitance, and capacitor is a device which can store charges, right? A capacitor is a system of two conductors separated by an insulator. This insulator can be air, it can be vacuum, or it can be any other insulating medium. Insulator means what? Insulator means dielectric medium. It could be a dielectric medium, it could be normal air, like air as well. Okay, usually in practice two conductors have charges plus q and minus q. The charges can be generally they have a charge separation like this, with potential difference V equals to V1 minus V2 between them. So for example, here we have two conductors. One conductor is this one, another conductor is this one. This one has a charge q, this one has a charge minus q. Potential of this one is V1, potential of this is V2. So what is the potential difference between these? So potential difference between them is V1 minus V2. Now obviously one of them can be minus, so total potential can be positive, because we know that potential can be negative. Unlike in electric field we only consider the direction, not the sign. So this is very important point to just to remind you. Q is called charge of the capacitor. Now even though the charge is Q and minus Q, we will say that charge stored in the capacitor is Q. It is not 0, by the way. So remember, this is very important point. Q is called charge of the capacitor, though this is in fact is the charge on one of the conductor. So this is the charge on one of the conductor, but if I say charge of the capacitor, that means only the positive sign, that is Q. Okay, the total charge of the capacitor is 0. Very important point, the total charge of the capacitor is 0. So if there is an MCQ question based on this concept, make sure you read the question very carefully. So if it is mentioned total charge, then total charge will be 0, no matter what. So generally there is a MCQ question where they will give you something like that. There is a capacitor like that, Q minus Q, and they will say what is the total charge stored in the capacitor. In that case you have to answer total charge stored is 0. If the same question is being asked and they ask you what is the charge of the capacitor, then it will be Q. Charge of the capacitor Q, total charge of the capacitor 0. So if the total word is there, so this total word is there, then total charge is 0. If only total charge is not there, then it will be Q. So be very, very careful, read the question carefully before answering. This question is being asked in one of the previous year, I think in for preparatory exam, the district preparatory exam, one of the district, they asked this question. So be very, very careful. Okay, the electric field in the region between the conductors is proportional to the charge Q. That is, the charge on the capacitor is say doubled, the electric field will also be doubled. Now what is the electric field between two plates? Electric field will be obviously from positive to negative, right? So if you increase the charge, electric field will also be doubled. So you can say that this electric field is proportional to the charge Q. So electric field between the plate is proportional to Q. So this is also a point for an MCQ, potential MCQ question. Okay, remember that electric field is proportional to the charge Q, right? Clear? Now let's move on. So very simple thing, capacitor means, let's summarize this page. Capacitor means two conductors, one having charge Q, one having charge minus Q. Okay, when we say charge of the capacitor, it is only Q. If we say total charge of the capacitor, it is 0. And the electric field between the capacitor plates is directly proportional to the charge Q. Okay, now let's move on. The potential difference V is proportional to Q and the ratio Q by V is a constant. So the potential difference. So we have generally we always use parallel plate capacitor, even though capacitor does not necessarily mean parallel plate. That's why they have given you that weird diagram. So parallel plate capacitor, we will come what is parallel plate capacitor. But if I say that this is a capacitor plate, this plate has a potential V1, this one has a potential V2. So what is the difference in potential? Difference in potential is V1 minus V2. This one is plus Q, this one is minus Q. Okay, so this potential difference, that is V, is proportional to Q. Okay, or you can say that charge stored is actually proportional to potential V. So Q is proportional to the voltage difference. That is, when you apply across, suppose you have applied a battery across it. Okay, so there is some potential difference. So this is the potential difference between the plates, and the charge that is stored over here is proportional to this potential difference. Okay, so Q is proportional to V. Q is proportional to V. And if you want to remove this proportionality, you have to add a constant of proportionality, that is Q is equal to CV. This C is obviously constant. It is the ratio of Q upon V. This constant is called the capacitance of the capacitor. So this C is called capacitance of the capacitor, very important term. So this is basically determines how much charge the capacitor can store in it if the potential difference is constant. So if you keep the potential difference constant, QC becomes Q. So that means it actually determines how much charge can you be stored inside the capacitor. That's why it is called capacitance, right? You have to have a high capacitance. So that means if the teacher is teaching well, then you should learn well and you should memorize well. Your capacitance should be high, right? So the voltage I will provide, but capacitance should be on you. So if you are a good capacitor, you should be able to remember well, you should be able to understand well, and then you can retain a high amount of charge inside you, right? Clear? So the SI unit of capacitance is farad. SI unit of capacitance is farad. Okay, we can find the dimension as well. Dimension of charge is A into T. Dimension of voltage. What is voltage, by the way? Voltage is energy per unit charge. Voltage is energy per unit charge. Okay, so from energy also you can come to the dimension of capacitance, but energy per unit charge. So what is energy per unit charge? So that is also AT. So it becomes A square T square divided by what is the dimension of energy. What is the meaning of energy? Energy is work done, right? Work done means force into length. So what is force? Force is ml t to the power of minus 2, and there is one more extra 2 because of the multiplication of length, right? Work done is ml square t to the power of minus 2. So from there you can find the dimension of capacitance m to the power of minus 1, L to the power of minus 2, t square, sorry, not t square, just a second, I don't know why the eraser is not coming. So it becomes, so dimension becomes m to the power of minus 2, L to the power of m to the power of minus 1, m to the power of minus 1, L to the power of minus 2, t to the power of 4, minus 2 goes up, becomes plus 2. So plus 2 is 4 into a square. So this is the dimension of capacitance. You should remember that as well. Okay, you should remember that as well, but we can find it in other way as well. We will explain that in the whenever that page comes. The capacitance C depends only on the geometrical configuration, that is shape, size, separation of the system of two conductors and type of insulating medium between the conductors. So very, very important, capacitance does not depend on charge and voltage. So there is a MCQ question where they are asking that capacitance is charged by voltage. If voltage is doubled, what will happen to the capacitor? Capacitor will remain constant. Capacitor does not depend on voltage or charge because it's a property of the capacitor itself. It is not the property of voltage or charge. That is very, very important. It comes from the fact that this is a proportionality constant, and that's why capacitor for a given capacitor is always constant. Capacitance for a given capacitor is always constant even if you change voltage or charge inside it. Okay, so it is independent of that, only depends on shape, size, separation and the insulating medium between the plates. Okay, from the above equation we can see that a large C V is small for a given Q. So if you can keep the capacitance high, okay, by applying small voltage you can store a large amount of charge, right? So that's why that is a good capacitor. So this means a capacitor with a large capacitance can hold a large amount of charge Q at a relatively small V. This is of practical importance. In practicality, we want the capacitor to be having a high value, where applying small voltage it can store a large amount of charge. So that is the practicality of this portion. So basically, if you see, capacitor is one of the most widely used equipment that we see in our day-to-day life. There are other components as well, but capacitor is one of the widest used you can say electrical instrument. Okay, for example, starting from your fans, ACs, your mobile phones, computer, laptops, everywhere capacitor is used, right? So that's why we have to have a basic knowledge about capacitor. So if you are studying electrical or electronics in future, you need to know about capacitor in detail, right? Let's move on. A high potential difference implies strong electric field around the conductor. So we know that electric field is basically dV by dx with a negative sign. So that means if you increase the voltage, voltage difference is high, that means electric field will also be high, right? Electric field is directly proportional to potential difference, negative of the potential difference, but if you ignore the sign, you can say that electric field is directly proportional to potential difference. A strong electric field can ionize the surrounding air. So the charges produced due to ionization are accelerate towards the oppositely charged plates. This partly neutralizes the charge on the capacitor plates. The charge of the capacitor leaks away due to the reduction in the insulating power of the intervening medium. So what does that mean? So capacitance cannot have an infinite value, which is important. So if you are applying some electric field between the plates, so this is positive, this is negative. As I mentioned, electric field is always from positive to negative, and if that is the case, if you are increasing the electric field very, very high, and if you have air or any other medium between the plates, at the presence of high electric field, the intervening medium ionizes. Ionizes means, suppose we are using air. Air is easy to understand, that's why I am using. So air has, say, oxygen or nitrogen. So nitrogen will become a nitrogen plus ion and an electron. Okay, so nitrogen, that is the most abundant element in air. So nitrogen will become a nitrogen plus element and an electron. So electron will move towards the positive plate, nitrogen plus will move towards the negative plate, and basically that what that does that do, it will basically reduce the charge. So this so basically it is similar to that of the, if you remember in chemistry you have studied electrolysis, so it is very similar to that that thing. So the nitrogen will come over here, absorb one electron, become nitrogen again. This electron will go here and it will reduce the positive charge by 1. So negative positive both are getting reduced by 1. So that's how what happens, the charge that is stored inside the capacitor plates reduces. Okay, and if you are using any other medium also, in that case also at high electric field, it can still ionizes that medium and this process still can happen, and that's why you cannot store infinite amount of charge in a capacitor. It has a limit. Okay, so this is very important point to understand, that you cannot create an infinitely large capacitor. Okay, because if you do so at the high voltage, the charge will start leaking and you will not have a constant charge, right? Constant charge stored in the capacitor, amount of charge stored will reduce. So that's why it is always required to know how much maximum charge that you can store in a capacitor. Okay, now if you want to study from us in a live lectures schedule with the proper structure and everything falling in place, then you can join our paid batch Pariksha Veera. The classes are already started and the batch price is 3499. You can click on the description section and join the batch. I will discuss more details about the batch at the end of this lecture. Right, let's continue. The maximum electric field that a dielectric medium can withstand without breakdown is called dielectric strength. Okay, so dielectric strength means the maximum amount a capacitor can withstand. Now I hope that you have seen this kind of elements in many circuits. Okay, when I was a kid, we had a cathode ray tube TV, CRT monitor, CRT TV. Okay, nowadays it is all replaced by flat screen, either LCD or OLED or AMOLED displays, right? So those things are not there. So whenever there is a breakdown in our TV, the mechanic used to come, he used to come take out the motherboard and he used to fix something like this. So I was wondering at that point of time, I was a kid, so I was thinking what is happening, what is he is doing. Basically he is just replacing a capacitor. Capacitor has basically lost its charge storing capacity, and that's why it needs to be replaced. So that's what the thing used to be done in the past. Nowadays the flat screen TVs that we use are very much efficient, so you do not need to change the capacitor every now and then. But still, if you open them, you still find such components present inside them. Okay, if you see a old say laptop or PC motherboard, you will still find these kind of elements present in them. Basically they are all representing separate capacitors. All this kind of, obviously not all of them are same. Based on the usage, there are different parts, but capacitors always have a positive and negative edge. Okay, so they all have a positive side and negative side. So that is very important part. In when we study resistor is obviously not part of the syllabus, but for resistance, positive negative sign is immaterial. You can apply it like any way you want, but for capacitor there will always be a positive side and a negative side similar to that of a battery. Okay, the dielectric strength of air is about 3 into 10 to the power of 6 volt per meter. For a separation between the conductors of the order of 1 centimeter or so, this field corresponds to a potential difference of 3 into 10 to the power of 4 volt, which is 30,000 volt between the conductor. Okay, there is a limit to the amount of charge that can be stored in a given capacitor. So that's what I'm saying, that it, so if you are applying this much voltage at a 1 centimeter difference, if the difference if you reduce this distance, then it can be something like something little bit more higher, but dielectric strength is about 3 into 10 to the power of 6 volt per meter. It is fixed for given material. Okay, for air it is this value, for certain other material it will be some other value as well. But one important point is that there is a limit of the amount of charge that can be stored. If you store more than that, voltage will exceed and the capacitor will break down and it will stop working properly, right? So without significant leaking in practice. So that means capacitor cannot store infinite amount of charge. As I mentioned, a farad is a very big unit. Okay, so if you are considering 1 farad, that is basically a huge amount of unit for capacitance. That's why in practicality we use units such as microfarad, which is 10 to the power of minus 6, nanofarad 10 to the power of minus 9, even picofarad 10 to the power of minus 12. So these are the farads that is more often used in electrical circuits. Microfarad for fans, ACs, etc. This is the 1 microfarad range. Okay, even electric motor which pumps water from ground level to top level, they also work in the microfarad range. Nanofarad and picofarad, they are used in electrical gadgets. Okay, starting from your mobile phone, laptop, PC, everywhere you will see these capacitors. This is a circuit of a motherboard. I have taken from somewhere, I don't know, but yes, so this is the motherboard. Here you can see a lot of capacitors are connected inside the circuit, right? So a lot of other things are there. These are the resistors. Okay, just for your general curiosity, this is resistor, this is a diode. Okay, and these are all capacitors. So you can see how many capacitors are there. Okay, obviously there are multiple components present inside this, but you can see the capacitors present in the circuit, right? Now let's move on, just for your curiosity, just to build some interest if you are feeling bored, right? Let's move on. The parallel plate capacitor, one of the most important concept from this chapter. A parallel plate capacitor consists of 2 large plane parallel conducting plates separated by a small distance. The space between the plates can be filled with dielectrics to increase its capacitance. So if you see that, here we have a, now when we started with arbitrary shaped conductors, right? We said they are arbitrary shaped conductors. Now that is very difficult to understand, so that's why we are now moving into parallel plates. Parallel plate means there are 2 plates, one plate is like this and there is one plate like this. So this is the 3-dimensional picture. Okay, and this is a 2-dimensional picture. Obviously this you cannot draw it like that. So basically 2 parallel plates. If you consider plates, you have seen plates, right? So that plates, if they are parallel and they are very rectangular, then they are called parallel plate capacitors. So if you keep 2 parallel conductors like that and the distance between them is kept small, it can be filled with air, it can be filled with anything else. In practicality, it is filled with some material other than air. Obviously air is very the dielectric strength of air is not very high, so you do not use air in between the plates. Also keeping air between the plates, keeping the distance between them is very small, is difficult. That's why either we will use mica or we use a very common thing is wax sheet. Okay, wax sheet is the same thing, that is the butter paper. You may have seen that butter paper, okay, which is being wrapped, butter is being wrapped using that sheet. So that kind of sheet is also used between the plates of a capacitor, right? So that's how the capacitor basically works. We will see that how to find the capacitance of the capacitor. So that is very important derivation, 3-mark derivation, which is important. So here you see that the charge density, suppose we have a 2 capacitor plates. Okay, one plate is here, one plate is here. Now here, if you see, this plate is plate number 1, this plate is plate number 2. This is storing positive charges, this plate is storing negative charges. Okay, I hope it is clearly visible. So if you see that this is positive charges, all the charges are positive, and here all the charges are negative. Okay, and if we know that if there is a conductor having some charges, there will be a charge density as well, right? A charge per unit something. Now here, because it's a plate that is a 2-dimensional surface, that means it will have a surface charge density. So surface charge density for the positive plate, if it is sigma, the surface charge density for the negative plate, it will be minus sigma, because for parallel plate capacitor, not only they are parallel, they are identical as well. Identical means the area of this plate and area of this plate must be same. And also by the definition of capacitor, we know that if charge stored in this is Q, this will be minus Q, right? So Q by A, here minus Q by A. Charge density, if you remember, surface charge density is charge divided by area. We have discussed that in our first chapter, right? So surface charge density is charge divided by area. So from there you can basically calculate what is the charge stored charge density for the first surface, positive surface, which is sigma, and charge stored in the negative surface, which is minus sigma. Okay, so plus sigma and minus sigma. Now we also know that electric field near a charged surface, is given by sigma by 2 epsilon naught. That is also done in our first chapter, but that case it was infinitely long charge sheet. Here we are using the concept that it is a very close to the charge surface. The distance between these two plates are very small. So any point near the charge surface, it will be sigma by 2 epsilon naught. So sigma by 2 epsilon naught here, sigma by 2 epsilon naught here, and sigma by 2 epsilon naught here as well, due to positive charge. Due to negative charge, here it will be minus sigma by 2 epsilon naught. Now what about this one? So this one, it will be not minus, but it will be plus. Why it will be plus? It will be actually minus of minus sigma by 2 epsilon naught, and this will be minus sigma by 2 epsilon naught. So for electric field, we always say that we do not consider the magnitude, we only sign, we only consider the direction. Okay, so if you are really wondering, so electric field due to positive charge will be away, electric field due to positive negative charge will be towards, so they basically gets added. For outside the plate, here it will be away, here it will be towards, so they will cancel. Okay, in the region 1 and 2, so this is region 1, this is region 2. So in 1 and 2, electric fields are basically opposite. Why opposite? So suppose this is the plates, this is positive, this is negative. So this is region 1, this is region 2, right? Now what happens, because many students confuse here only and then they started thinking physics is hard. Actually it is not. So let's see. So for positive charge, what will be the direction of electric field over this region? Positive charge electric field will be away always, no matter what. If you are coming over here, it will be also away. Okay. Now for a negative charge, what will be the direction of electric field? For negative charge, if you are considering this region, it will be towards. This region will also be towards. This region it will also be towards. This region it will also be towards. Okay. No matter where it is, when you are considering the negative plate, you can ignore the positive plate, only focus on negative charges. When you are doing the positive charges, positive plate, you ignore the negative plate and only find what is the direction due to the positive plate only. So do not confuse. So when you are considering the positive plate, cover the negative plate, see what is the all the direction. When you are considering the negative plate, cover the positive plate and see whatever all the direction is, right? So if you see that here they are equal but opposite, here also equal and opposite, here they are equal but in the same direction. Inside the plate it is equal but in the same direction. So outside they cancel each other and become 0. Inside they are equal and in the same direction, so they gets added and the electric field becomes sigma by epsilon naught. Right, electric field becomes sigma by epsilon naught. Now we know that electric field is minus dV by dx. Magnitude wise, we can write dV equals to E into dx. Magnitude wise, right? Now if the electric field is constant, potential difference is constant, then we can write the same thing as V is equal to E into x. Now here x is basically the distance between the plates, which is given by d. The distance between the plates, which is given by d. So instead of writing x, we will use d. So that is what it is written over here. So V is equal to E into d. Okay. Now put the value of electric field over here and you get sigma d by epsilon naught. Right. Now we also know that what is the total charge stored in the capacitor plate? Total charge stored in the capacitor plate is Q. Then Q sigma is equal to Q upon A. I have already informed in the previous page. So Q is equal to sigma is equal to Q upon A. So Q equals to so if you put that sigma's value over here, you get Q d divided by A epsilon naught. Okay, you get Q is Q by A D into epsilon naught. What is this happening here? We are basically substituting the value of sigma in this equation. Sigma is charge density is total charge divided by total area, right? So just substituting that, and now we will compare this equation with our original equation, Q is equal to CV, and from there we see that value of C is coming out to be A epsilon naught by D. So this is the expression for capacitance due to a parallel plate capacitor. This is a 3-mark question for your board exam, for your midterm, for your FA1, everywhere. This is one of the most important concepts, right? Now let's move on. Effect of dielectric on capacitance. Okay, so now so far we are using air. That's why the formula also, if you go back here and check the formula here also, A epsilon naught by D. That means inside the plate was air. Okay, inside the plate was air. Now if you insert a dielectric medium such as this, what it will do? It will polarize itself. The dielectric medium will polarize itself, and then what will happen to it is it will actually increases the capacitance. How? Instead of using sigma naught, we have to use only sigma. Okay, so epsilon naught, sorry, instead of using epsilon naught, we have to use only epsilon, and epsilon is basically what is dielectric constant into epsilon naught. So epsilon for any medium is given by dielectric constant into epsilon naught. So if you just substitute that back into this equation, you get A into K into epsilon naught. So basically the new capacitance is Ka times the old capacitance. So if they ask you that a dielectric medium of dielectric constant 2 is inserted between the plates, what will happen to the capacitance? Capacitance will be doubled. Okay, so based on this also we have seen a lot of questions in the past. So just check this question. A parallel plate capacitor of capacitance C1 and with the dielectric slab between its plates is connected to a battery. When the dielectric slab is removed, keeping the capacitor connected to the battery, the new capacitance and potential difference are C2 and V2 respectively. Then what is the following correct relation? Now let's see that we have a capacitor, it is connected to a battery. Initially there was a dielectric medium between the plates, right? Initially there was a dielectric medium, suppose the capacitance is C1. Now when you remove this dielectric medium, what happens is that capacitance decreases. If you remove the dielectric medium, the capacitance will decrease. So that means C1 is greater than C2. No doubt about it. First one is capacitance with dielectric medium. So capacitance was higher. Now you have removed the capacitance. That means the capacitance will decrease. So now the new capacitance will be smaller than the previous capacitance. So C1 is greater than C2. There is no doubt about it. What about voltage? So because it is still connected to the same battery, the voltage across the capacitor remains same. Only capacitor changes, charge will change, but the voltage here will remain same because the capacitor is still connected to the battery, same battery. So remember that if battery is not removed, then the voltage remains same. So voltage remains same, but capacitance decreases. So correct answer is option B, V1 equals to V2, C1 greater than C2. So this is the answer for this question. So very easy question, analytical question. If you just understand this concept, you should be able to answer it within 30 seconds, right? Reading the question and solving should not take more than 30 seconds if you are clearly aware of it. Now combination of capacitors can be connected in two different ways, same as resistances. Series combination means capacitors are connected one after another. So suppose this is C1, C2, C3, C4, Cn. Okay. Now in exam, they will ask you two capacitors are connected in series. Might ask, not definitely will ask, but might ask two capacitors are connected in series. Find their equivalent capacitance. How to do that? So we will use, even though that is the series combination, this is general series combination. So first we will derive the theory for two capacitors, then we will generalize for n number of capacitors. C1 and C2, they are connected in series, and whenever you are connecting in series, there has to be some source. So this voltage source is connected with the capacitor. Okay, so C1 and C2 are connected with this voltage source V. Now how to do that? So suppose now in series combination, what is constant over here? So if you see that when the charge is flowing, when the charge is being flown, the same charge will be flowing through C1 and C2. So when the capacitors are charged, both of the capacitors should have the same amount of charge. Okay, the flow of charge, because charge is a conserved quantity in an isolated system, the total charge must be constant. So that means charge must remain same. So because when the charge, whatever charge is entering over here, the same charge is passing through C1 and the same charge has to come out of C2. That means charge stored in the both of the capacitors should remain same. So that is the property of series combination. Voltage difference, however, will be different. Voltage difference, however, will be different. But voltage is also a quantity which is basically representing energy. So that means energy should also be constant. So total voltage that you have applied must be sum of these two individual voltages. Okay, must be sum of these two individual voltages, because voltage comes from the energy term, right? So now from here we can say that Q equals to C1 V1, again Q equals to C2 V2, right? So both Q's are same, Q is equal to CV. So from there we can write that V1 equals to Q upon C1 and V2 equals to Q upon C2, right? Now from there, from combining this equation and these two equations, we can write V equals to Q upon C1 plus Q upon C2, or Q is common, we get 1 by C1 plus 1 by C2. So this is our equation number 1. Now this is not our target. Our target is to find the equivalent capacitance. What is equivalent capacitance? So if you replace everything with a single capacitor, no matter how many capacitors are there and how they are connected, if you can replace them using one capacitor, that capacitor is called equivalent capacitor. Equivalent capacitor means no matter how many originally are there, if you are to replace them with a single capacitor, that capacitance of that capacitor is called equivalent capacitor. Here we have two capacitors, so every other condition should remain same. So voltage V should remain same over here. Now as I mentioned that the charge is invariant, charge is constant, the same amount of charge should pass through the equivalent capacitance as well. So equivalent capacitance should also store the same amount of charge when applied the same amount of voltage, right? So from here we can write Q equals to C into V, or C equivalent into V, or V equals to Q upon C equivalent. This is our equation number 2. So if you compare equation 1 and equation 2, you get Q upon C equivalent equals to Q into 1 by C1 plus 1 by C2. That means 1 by C equivalent equals to 1 by C1 plus 1 by C2, right? And from here you can generalize for n number of capacitor. 1 by C equivalent equals to 1 by C1 plus 1 by C2 plus 1 by C3 plus ... 1 by Cn. Okay, this is the general formula for capacitors connected in series. Now for this, it can be written directly C equivalent equals to C1 C2 by C1 plus C2. This is very handy for solving numerical question. If they ask you theory, you can leave your answer over here, but for numerical, if you remember this formula, this is very handy to solve questions quickly. Okay, next is parallel combination of capacitors. It is easier than series combination. In parallel combination, capacitances are connected like this. This is the general combination. Okay, so this is the general combination. Obviously, lot of capacitance are there. Lot of capacitors are there. Okay, and just a second. And there is a battery as well. Now, difference between a battery and capacitor, don't be confused. Battery is denoted like this, some students confuse, and capacitors are equal. So that is capacitor, this is a battery. So don't get confused between a battery and a capacitor. Okay, so this is all C1, C2, Cn, all of them are connected like this. This is called parallel combination. Again, parallel combination also they will ask you for two parallel combination, two capacitors are connected in parallel, find the equivalent capacitance. So how to do that? C1 and C2 they are connected in parallel with a battery. Now in parallel combination, as you can see that whatever voltage that you have applied across this battery is equally applied on C1 and C2. So voltage difference is same for both the capacitors because they are connected in parallel. Parallel means voltage is same, series means charge or current is same. Okay, this is valid for capacitor as well as resistors. Okay, so just remember, in case of parallel combination, voltage remains same. For series combination, current remains same. Okay, or charge remains same. Okay, so same voltage is applied across this one, same voltage is applied across this one. So voltages are same. Now suppose this one is storing a charge Q1, this one is storing a charge Q2. So what is the total charge? What is the charge Q1? Q1 is equal to C1 into V and Q2 equals to C2 into V. So what is the total charge? Total charge is Q1 plus Q2, that is Q equals to C1 plus C2 into V. If you add these two over here, you get total charge stored in the capacitance, that is C1 plus C2. Now if you replace these two capacitors using a single capacitor, that will be our equivalent capacitor. So this will be our equivalent circuit where only single capacitor is there. So no matter series or parallel, equivalent circuit always will have only one capacitor present. Okay, so this is our equivalent circuit. Now what is the charge stored in an equivalent circuit? So as I mentioned, equivalent circuit should have the total charge of the original case and the voltage applied should also remain same, right? So if you apply same amount of voltage, if it is storing the same amount of charge, then it is called equivalent capacitance. So in this case, the total equivalent capacitance is C equivalent, charge stored is Q. So from here we can write Q equals to C equivalent into V. So now compare, this is our equation 1, this is our equation 2. Comparing 1 and 2, we can write C equivalent V equals to C into V1 plus V2. So sorry, what I am doing, it is C1 plus C2 into V. So V cancels and we get C equivalent equals to C1 plus C2. So as you see, this is much more easier than the parallel combination. So what is the equivalent capacitance for n number of capacitors in series? So that will be C equivalent is equal to C1 plus C2 plus C3 plus plus Cn. So in case of series combination of capacitor, capacitance increases. So if you are facing a situation where you have to increase the capacitance, you have to use series combination. In some situation where you want to decrease the capacitance but you want to increase the load, the voltage, because voltage is basically distributed between them. So if you are in a situation where suppose the individual capacitances cannot handle a large amount of voltage, you want to make them having a high voltage compliant device, then you have to connect them in series. So series combination is used to make it voltage compliant, low value capacitance, whereas parallel combination is used for high value of capacitance. Their combination, series and parallel, are used when individual capacitors have a less voltage compliance. So first you connect them in series. There is a question there in KCET PYQ, we will solve it. So there is a question where they are being asked that capacitors are connected in capacitors are given where they ask you that how they has to be connected so that the overall voltage increases, overall capacitance increases. So in that case, to increase voltage you have to connect them in series, to increase capacitance you have to connect them in parallel. Okay, now let's see one question. An electrician requires a capacitance of 6 microfarad in a circuit across 1.5 kilovolts. So this is the voltage requirement. A large number of 2 microfarad capacitors which can withstand a potential difference not more than 500 volt are available. the minimum number of capacitors required for the purposes. So exactly the same question that I was talking about. So here the voltage that we need, the requirement is 1500 volt, right? The requirement is 1500 volt, right? But each capacitor that can only handle 500 volt. So we require a circuit where the capacitor should handle a 1500 volt voltage, which is 1.5 kV. 1.5 kV is nothing but 1500 multiply by 1000. You will get convert this into kV, right? And given the rating of the capacitors are only 500 volt. Also, we need a higher value of capacitance than the given value of capacitance. So we basically require first stage is to make them voltage compliant, then make them capacitance compliant. How to increase the voltage? To increase the voltage, always you have to connect them in series. And how many of them you need to connect them in series? For that you have to divide 1500 by 500. That is the only role of these voltages. Otherwise, for this problem you do not need to know the exact voltage. Okay, so you need 3 capacitances connected in series, so that individually each of them can handle 500. Okay, each of them can handle 500, so that the total voltage rating becomes 1500. Okay, but when you connect them in series, what happens to the overall capacitance? Overall capacitance decreases. So this one was C, this one was C, this one was C. Suppose, what happens to the overall capacitance? So 1 by C plus 1 by C plus 1 by C. So basically, just remember there is a shortcut formula for when equal capacitances are connected in series. The equivalent capacitance can directly be written as capacitance by number of capacitance. Okay, so here when you connect all of them in series, the equivalent capacitance becomes C by 3. 3 capacitors, C value is known, I will use it, don't worry. C value is 2 microfarad. Okay, so this is the C value, this is the equivalent C value, this is C equivalent. Okay, this is the C equivalent, this is given C. Okay, so now as you can see, the overall capacitance decreases. Now we have to increase the capacitance. How can we increase the capacitance? Now we have to use similar combination of capacitance. We have to use similar combination of capacitance in parallel, so that our voltage requirement is still being met, but our overall capacitance increases. Okay, overall capacitance increases, but our voltage requirement still met. And suppose here we connect them, say n number of such capacitors, we connect them in parallel. Okay, so individually each of them have a capacitance of C by 3. N such capacitance are connected in parallel. So what is the total capacitance? In case of parallel, they gets added. So 1 plus 1 plus 1 plus 1, basically if you add them up to n times, it becomes n into capacitance of 1. So n into C by 3, and that should give you our C equivalent. That should give our C equivalent. So when you are connecting in series, voltage increases. When you connected them in parallel, capacitance increases. So remember, in case of series combination, if they are equal, directly you can calculate by C by N. Okay, so 3 capacitances connected in series, equivalent capacitance is C by 3. When equal number of capacitances are connected in parallel, then you have to multiply. Okay, in case of series, divide, in case of parallel, multiply. So that is equals to, so now we will put the value. We do not know the value of n, by the way. So 2 by 3 in equals to 2 by 3 equals to 6. So from here n will come out to be 6 into 3 by 2, that is 9. So the value of n is 9, but that is not the number of capacitors required. So we require 9 such line, 9 such capacitance line, so that the equivalent capacitance becomes 6 microfarad. Each line has how many capacitance? Each line has 3 capacitors. So total number of capacitors, the total number of capacitors will be 3 into n, that is 3 into 9, that is 27. So we require 27 such capacitors to fulfill our requirement. This is very interesting problem, one of my personal favorite problem. Okay, now let's move on. Energy stored in a capacitor. So now derivation of energy stored in a capacitor is not there, but conceptually what it is. So if you have a parallel plate capacitor, starting with parallel plate capacitor, you take out a small amount of negative charge, and the electric field is from positive to negative. The electric field is from positive to negative. So if you take a negative charge from the negative plate and try to push it towards the positive charge, you have to do some work. Okay, you have to do some work, and that work is basically stored inside the capacitor. That is called energy stored in the capacitor. The expression for energy stored in a capacitor is given by, the energy stored in a capacitor is given by half CV square. Okay, half CV square, or it can also be written as half Q into V, half Q into V. Okay, or it can also be written as energy stored equals to half Q square by C, half Q square by C. So all of them are energy stored in the capacitor. Okay. Now what is about energy density? Now from this expression you can find the dimension of capacitance. Okay, from this expression you can find the dimension of capacitance. I was talking about this only earlier. So from this particular equation it is very easy. So capacitance is basically half Q square by E, right? If you use cross multiplication you will get that capacitance equals to half Q square by E. Now if you are considering the dimension of capacitance, okay, that will be dimension of Q square by dimension of E. What is the dimension of Q square? A square T square, and dimension of E is mL square T to the power of minus 2. So the same expression that we have got earlier, m to the power of minus 1, L to the power of minus 2, T to the power of 4, A square. So this is the dimension of capacitance. Okay. Now one more important thing is that energy density, which is basically energy stored per unit volume. Energy stored. Now one small mistake that I have made in this chapter, electric field is denoted by E. So energy we will denote by capital U. Energy we will denote by capital U. Okay, so that is one small mistake that I have done. This will be U. Okay, here also it will be U. Okay, now energy density is small u, which is basically the total energy stored divided by volume of the parallel plate capacitor, and that will turn out to be half epsilon naught C square. Okay, it will turn out to be half epsilon naught half epsilon naught E square. It can be easily derived, but you don't need to do the derivation. Okay, here this E is electric field. This is electric field between the plates. Now that is one important point to remember, that energy basically between the capacitor plate is stored in the electric field. In the capacitor plate, the energy is stored in the electric field. So if you increase or decrease the electric field, the energy stored will change. So energy density actually represents how the energy is stored. So energy is stored in the electric field. You can do the derivation. Derivation is not part of the syllabus, but the final formula is still part of the syllabus. So you have to remember it. Okay. Now let's move on to one question. In the figure, charge on the capacitor is plotted against potential difference across the capacitor. The capacitance and the energy stored in the capacitor are respectively. So here there is a diagram given, Q versus V. Okay, and they ask you what is the capacitance and what is the energy stored. How to do that? First, let us calculate the energy stored. Energy stored is easy. It is half Q into V. So if you see that at this point, charge and voltage, both things are given. Charge is given in microcoulomb, so that only that is that thing you need to be little bit careful about. So energy stored will be 120 into 10 microjoules, because the charge was micro, so this will be microjoules. Voltage was in volt, so energy stored will be microjoules, so it will be 60, that is 600 microjoules. So this is the energy stored. What about the capacitance? Capacitance is given by Q upon V. Q was 120, voltage is 10, that will be 12 microfarad. Again, because the charge was microcoulomb, so the capacitance will be 12 microfarad. So 12 microfarad, 600 microjoules. So option C is correct. Just solve it, easy question, don't worry, you should be able to solve it. So don't be afraid if you see some kind of graphs is there, how to do it. There will be a point where the values you can find from the graph. Okay, so that point only you need to use to solve the question. Any other points you can skip, no need to worry. Now some daily practice paper question, 2 daily practice paper question is there in this chapter. A conducting sphere of radius r is given by a charge q. The electric potential and the electric field at the center of the sphere respectively are. Interesting question. Try to solve it and mention the answer in the comment section below. And if you still are not able to solve it, that also you mention in the comment section below. I might discuss that in our future lectures. Right. Next, work done in carrying an electron from point A to point B in an electric field is 3.2 into 10 to the power of minus 18 joules. The potential difference VB minus VA is. Okay. So point A to point B, the electric field is given. Okay, and it is an electron. So electron means charge of an electron is also known. They ask you what is the potential difference. Actually easy question. Just little bit be careful and solve it. Okay. Now before I end this class, just to remind you that our Pariksha Veera batch is going on in full swing, where we are teaching all subjects, physics, chemistry, maths and biology in this Pariksha Veera batch, where you will get full PU2 coverage with the KCET preparation. Okay, and that will be each subject will be having more than 110 plus hours of classes. Also there will be 20 plus part and full length tests per subject, which is very, very important. You will get teacher notes, assignments, unlimited DPP generator, everything will be provided, delivered on the web, on the Vedantu app. So web platform is a wonderful platform where you can learn with engagement. It is a lot more engaging than YouTube, obviously. And if you want to get a feel of the web app, you can go into our all-in-one page. You just need to click on the link below and click on buy now. It is 0 fees for our all-in-one page. If you want to purchase the Pariksha Veera batch, which is also in the same platform, the price is 3499. So to make you familiar with the web platform, we are giving you the ACE series absolutely free of cost. You can register for that as well. Also you will also get the link for joining the Pariksha Veera batch, that is also present in the comment section below. Right. All the best for your KCET preparation. I will be back with KCET PYQs very, very soon. That also will be recorded session. So till then, bye.